My name is Kevin Koyewe, and today I'm presenting my final year project proposal titled Spatial Interpolation of Second-Rank Polarization Tensor Across Different Domains under the supervision of Dr. Suzarina binti Ahmed Shukri. To start, a polarization tensor PT is a 3x3 matrix describing how a geometry inclusion responds to a background linear field such as electric or magnetic field. PT uniquely characterizes both the shape and material contrast of a hidden inclusion. Because of this property, PT is important for electrical impedance tomography security screening and landmine detection. While extracting analytical solution exists for simple geometry like spheres and ellipsoids, as shown in proposition 2.4. However, real-world application require advanced numerical computing. PT theory originates from Polarization and was modernized by Amari et al. Classical linear element interpolation are computationally efficient but shows limitation in accuracy on highly curved surface. Conversely, recent advancement quadratic element integration introduced by Shukri et al. Is highly precise but significantly raises the computational cost. This brings us to our core research gap stated that a symmetrical ellipsoid has non-uniform curvature. Some regions are highly curved while others are flatter. Currently, an adaptive scheme that dynamically combines both linear and quadratic elements has not yet been systematically developed. I am proposing a novel adaptive linear quadratic element integration scheme. Instead of uniform applying one element type, our algorithm will dynamically apply high precise quadratic element at high curvature surface and automatically switch to linear element on flatter surface. This perfect balance the precision and computational cost. The objective of this study are formulate the methodology for linear and quadratic element integration of ellipsoid, validate the numerical solution of the first order PT with analytical results, analyze the convergence and accuracy of first order PT for ellipsoid, develop an adaptive linear quadratic element integration for first order PT of ellipsoid. As detailed in the methodology flowchart, our process begins by defining geometry, discretizing geometry into triangular meshes, and generate nodal coordinates and point using DetGen. Once the mesh information is extracted into MATLAB, the code calculates the normal vector Gaussian weight and distance between midpoint of element and distance between Gaussian points for linear and quadratic element integration respectively. Then the K star B is computed followed by solving the linear system. Finally, output the final PT values alongside a relative error.
Moving on to our preliminary results, we execute multi-coordinate sphere modeling using a 44-element mesh across different spatial positions to ensure the MATLAB code accurately tracks the tensor's value in any space. We also tested 10 different conductivity ranging from poor conductor at K equals to 0.05 to highly conductive material at K equals to 100,000. This proved that our framework robustness across any material contrast. Crucially, our comparative error analysis verified that the quadratic element methods consistently yield a lower relative error compared to the linear methods. This strongly justifies our goal to build an adaptive framework.
In conclusion, this research established an optimized numerical framework for computing the first-order PT of symmetric ellipsoids. Built on these validated models, our proposed additive linear quadratic scheme is expected to achieve same high accuracy as uniform quadratic method while significantly reducing computational time. Once fully validated against analytical solution, this adaptive scheme will bridge the efficiency gap, ultimately improving the reliability and sensitivity of detection technology like